Hello everyone. In our last video, we learned about an important group of functions called exponential functions. And in this video, we're going to learn about the inverse of the exponential functions. And we discovered that exponential functions are one-to-one, and we know that all one-to-one functions have inverses. So this time we'll explore the inverse of those functions, and they're called logarithmic functions. As we saw last time, the exponential function has the form f of x equals b to the x for b greater than 0, b shouldn't be 1, and x should belong to the set of real numbers. We've depicted two of them here. One is showing an exponential growth curve, the other one is showing exponential decay. We know growth happens when b is greater than 1, and decay happens when the value of b is between 0 and 1. We also learned to solve some simple equations like this one, where it's possible to take both sides and write them as powers with the same base, because when we can do that, then we can use the fact that the exponential function is a one-to-one function, which implies whenever the outputs are the same, that means the inputs must have been the same. So we use this fact to conclude that this is going to imply this, because if two powers are the same and their bases are the same, then the exponents must be the same. So this was very helpful for these simple types of exponential equations. But if we take an equation even as simple looking as this one, we won't be able to use the same technique, because we can't write 15 as a power of 2. So for that, we're going to need the inverse of the exponential functions, and that's precisely what we refer to as a logarithmic function. So now we'll go ahead and formally define the logarithmic function. We're going to use the same restrictions on the base as we had for the exponential function. The fact that the base needs to be a real number that's greater than 0. It shouldn't be 1, and the x values this time should be positive, whereas for the exponential functions, they were all real numbers. We'll find out why when we look at the graphs. Now, the way we define logarithms is actually using the exponential function, because there's an equivalence here. So we say y equals log base b of x if and only if x equals b to the y. In other words, the entire logarithm becomes just the exponent here of this exponential equation. So these two equations are considered equivalent. So what that means is that they're different ways of saying the same thing, in very much the same way, for example, that you can say the cube root of 8 is 2, or you can say 2 cubed is 8. They're basically expressing the same fact, but in different forms. In fact, we call this left equation the logarithmic form of this equation on the right, and we call this exponential equation on the right the exponential version of this logarithmic equation on the left. So this will be the fact that you want to become very comfortable with as we proceed and use the concept of logarithms. And I will remind you of this on most of the pages that will follow. A couple of notational and similar types of notes. One is that when you see this expression log bx like that, you say logarithm base b of x. For short, you can just say log base b of x. In this expression, x is called the argument of this logarithmic expression. And since x equals b to the y and b is greater than 0, notice we're taking a positive number and raising it to a power. x will never become negative. So that's the main reason why we have this restriction, x is greater than 0. We'll see that again, as I said, when we graph it, it'll make more sense. So x can never actually become negative. That's why we need the restriction, x is greater than 0. And also notice that the restrictions that we have on the base of a logarithmic functions are the same restrictions that we had on the exponential function. Namely that the base should always be positive and it should never be 1. So now we're going to go ahead and look at an actual example with numbers. What you really need to understand about logarithms is that basically a logarithm is the invisible exponent kind of between these two numbers, where you need to raise this number to the power of that invisible exponent to get this higher number. So when you see log base 5 of 25, you're going to ask yourself a question. You're going to say, what power of 5 gives me 25? When you answer that question, you found the log. Remember, a logarithm is just an exponent. So one way of dealing with this is just like that, reasoning it out. Another way is you can go ahead and form a simple equation out of this. You can say log base 5 of 25 equals x, just give it a name, and then go ahead and use this conversion. So you see, when you want to go from this logarithmic form to this exponential form, notice the base of the logarithm, like here being 5, becomes the base of your exponential equation. The entire logarithm, which is x here, becomes the exponent, so to the power of x equals, and this in here is going to be the whole power, so 25. So now all we have to do is to solve this simple exponential equation, and we will know the answer. So 5 to the x, we know that we can solve this by making both sides the power of 5, and we end up with realizing that we have two equal powers and they have the same base, so therefore the exponents must be the same. So we get x equals 2, like that. Now, notice that the reasoning that we had in the beginning yielded the same result. So always be aware of the fact that the logarithm base 5 of 25 is just that exponent that you have to raise 5 to the power of to get 25. And that will always make this very simple for you. Just remember, logs are just exponents. So here's another example. As you start to get a little bit more comfortable with these, you should definitely try some on your own before you continue with the video. All right, so as fractions come in, etc., it might start to get a little bit trickier. So definitely set up the equation like we mentioned. So we have log base 7 of 1 over 49 that we're looking for. We'll just go ahead and call it x. Now we're going to use this relationship to convert this to an exponential equation. Never get attached to the letters. Understand the relationships. That's what's important. Someone should be able to switch all of those letters for you, and you should still be able to set up the right relationship, because it's the relationships that you are learning about. So here, notice if we're going to convert this using this relationship here that we have between the logarithmic and exponential forms of these two equations, we get 7 to the power of x equals 1 over 49. The easiest place to start, of course, is the base, because we know that the base of the logarithmic equation is also the base once you convert that logarithmic equation into its exponential equivalent. And The other thing that's easy to deal with is that you know that the entire log is going to be the exponent. That's why x, which is equal to the entire log, is going to go in the exponent position. That only leaves one other thing, which must be what goes on this side, and that's the argument. All right, so now we have 7 to the power of x. We know we can write 49 as a power of 7, but in order to be able to use this rule that b to the x equals b to the y implies x equals y, we have to have the other 7 on the right side on the top as well. So of course we'll need to utilize help from one of our laws of exponents, which, if you recall, said if you have b, for example, to the power of negative n, that's going to be 1 over b to the n. So using this rule, we can write 7 to the power of 1 over 7 squared as 7 to the negative 2. There were 2 versions of this, if you remember. The other one was 1 over b to the negative n equals b to the n. So you use whichever one is appropriate at the given time. For this case, since we have the positive power in the denominator, we're going to be using this one that we wrote first. But sometimes this one comes in handy. So you have to know both. So we get 7 to the power of negative 2. And now, of course, we can conclude that x must be equal to negative 2. Again, as we discussed when we did these in the previous video, this is not a basic event that's taking place here. We're not canceling the 7s or anything like that. We're using the fact that the exponential function is a one-to-one function, and these are 2 of its outputs, therefore the inputs must have been the same. Of course, the exponential function under consideration here would be f of x equals 7 to the x. All right, so here we have another problem to look at. Go ahead and try it for sure before you come back. Okay, so if we go ahead and again just give it a name. Once we do that, then we can go ahead and easily convert it to exponential form. Remember, the base, which is 100, is also going to be the base of the exponential equivalent, and the entire log, so all of that, which is x, is going to be the exponent, and the argument is going to be the whole power, so equals 1. So now we have to ask ourselves, 100 to what power could possibly be 1? And of course, again, as you can see, all this is very closely connected to the laws of exponents that we've already learned. So you need to know that any number to the power of 0 is 1, as long as that number is not 0. 0 to the power of 0 is undefined. So as long as you're not raising 0 to the power of 0, you should be fine. So here again, we can see that x is going to be 0. All right, so that was slightly different from the other ones we've done. So, but you need to know this rule. As long as you know this rule, you should be fine. Now we'd like to get some more practice converting between exponential and logarithmic forms of these equations. So let's take a look at a few problems that help us with that. All right, now we have 4 problems here that we're going to convert to exponential form. Notice they're all in logarithmic form, and now we're going to go ahead and convert them. Again, remember that the easy part about the whole thing is that the base of the logarithmic equation is also going to be the base of the exponential equivalent, and We know that the entire logarithm, which is 6, is going to be the exponent. And when you take care of that power, you're going to get the argument on the other side. So we get 1 million. Let's try that again. All right. So for the next one, as you know, same business. The base remains the base. The entire log, which is equal to -3, is going to be the exponent. And the power is going to be the argument. So it becomes really, really easy after a while if you practice it enough. All right, I hope you've definitely tried these before you've come to join me again. So here, of course, we're going to have 125 to the power of -1/3, which is the entire logarithm, which becomes the exponent. And on the other side, we're going to have the argument. So this one is an example to make sure you're not getting attached to these letters. So you should be able to convert this now, because you know where everything should go. So you know that u is the base, so that's going to be the base of the exponential equation as well. And w, which is the entire log, is going to become the exponent. And of course, the entire power is going to be the argument. And that's how we do these conversions. Okay, so now we're going to go in the other direction. We're going to start with the exponential form of an equation, and we're going to convert it to the logarithmic form of the same equation. So starting here, of course, we know that just like we did in the other direction, the easiest place to start will be with the base, because we know the base of the exponential equation is also going to be the base in the logarithmic form. So log base 2. Now let me put the equal sign, because I know the entire logarithm is going to be the exponent. So the 5 will go on this other side. And we know that the power, the whole power, which is 32, is going to be the argument. All right. Again, I hope you've tried this before you join me. If you haven't, you can pause now and try some. All right, so for the next one, we can see the base is going to be 1/3, because it's the same base as the other equation. We know the entire exponent, the logarithm, is going to be the exponent, so that'll be -4 on the other side. And the entire power will be the logarithm. All right. So for the next one, we have log, the base is 64, and the exponent is -1/3, so that's going to be the entire logarithm. And the power, which is 4, will be the argument. This is a good exercise to make sure you're not getting too attached to these letters, but rather are understanding the relationships. So you should be able to convert this now to logarithmic form. So we have log. Now this time we know the base is going to be L. We know that the entire log will be the exponent, so M will go on the other side. And the entire power is going to be the argument, so N will go in here. All right, so that's some conversions there for you. Make sure you get completely comfortable with these conversions before we proceed. All right, so now we're ready to go ahead and solve some simple logarithmic equations. Basically, they're going to be of this form, and you see how we have 3 letters involved. One of them will be missing, the other 2 will be given, and we'll be solving for the missing variable. As we start solving equations, we have to make sure that these restrictions are not violated. And of course, we're going to be using our conversion quite heavily as well. So here we have an equation for the first time. We're going to convert for the first time in the sense that we're solving. So far, we've just been converting. So we're going to go ahead and to solve these, the easiest thing is to go to a more familiar format, which is the exponential format. So we'll go ahead and write this equation in exponential form. So of course we get 5 to the negative 2 equals x. You could have just as correctly written x equals 5 to the negative 2. Makes no difference which side you put which one on, because these two equations are equivalent. All right, so now we go ahead and simply give the answer in a format that has no negative exponents. So we get 1 over 5 squared. So we get x equals 1 over 25. And that's as simple as these get. So if you want to write it as a solution set, you'll just write the solution set contains 1 over 25. Now, the least amount of checking that you'll want to do for a problem like this is to make sure that these restrictions are not violated. That's the minimum amount of checking you want to do. And especially when x is in the argument position or the base position, that's where the restrictions are. Remember, on this other side, you could get any real number. You could get positive numbers, you could get negative numbers, you could get 0. So the real places where things can go wrong are the base position and the argument position. Now we do notice that one is positive, shouldn't be posing any problem. Or we can do a complete check. We could just say log base 5 of, we're going to plug in 1 over 25 for x, and we're going to check to see if that's equal to negative 2. When we convert that to exponential form, we get 5 to the negative 2, and we want to know if that's equal to 1 over 25. And 5 to the negative 2 is, of course, 1 over 5 squared. We want to know if that's equal to 1 over 25. Finally, we get 1 over 25 equals 1 over 25. So it checks out, and we can move on to another problem. So that's how you do these. All right, so here we have another problem with a fractional base. So we go ahead and convert it to exponential form. Let me go ahead and write the argument by itself on the left side this time, just for variety. And on the right side, we'll get the base to the power of the exponent, which is going to be the whole logarithm, like that. So we get 2x plus 5 equals 1 over 27. And of course, you know that the easiest way to solve an equation like that is to go ahead and clear the fraction by multiplying both sides by the LCD, which is just going to be 27. And don't forget to distribute. So we're going to get 54x plus 5 times 20 is 100, 5 times 7 is 35, so 135 equals, on this side, of course, those cancel out, they just leave us 1. So we get 54x equals 1 minus 135. So x, let's go one more step, 54x equals negative 134. So x is going to be negative 134 over 54. I know at least 2 goes into them, so that should be negative 67 over 27. All right, so sometimes students take a look at that and I go, oh, it's negative. You know, Farzin said no negatives in the argument position, so that's no good. But that's not the problem, you see. As long as 2x plus 5 doesn't become negative, we should be having no problems. So if you want to quickly check that before, to make sure it doesn't become negative before you actually do a full check, you can always do that quickly on a calculator. Let's take a look. All right, so here we'll go ahead and multiply 2 by negative, we're going to plug in negative 67 over 27 for x, and then we're going to go ahead and add 5, and then we'll hit enter. Notice it remained positive, so yeah, barely. I mean, that's very close to 0, but that doesn't matter. As long as it's positive, we're good to go. So again, this was the minimum amount of check you should have done anyway. You want to make sure that this doesn't result in a negative number, because otherwise the argument would become negative, which is not allowable. As you know, x needs to be, well, in this case, when we say x, we're talking about the argument, so you have to always think generally. So that's why we have to check. All right, so if you want to do a full check, of course you can. You just basically have log base 1/3 of 2 times negative 67 over 27, and you want to know if that's equal to 3. So you want to know if negative 134 over 27. Oops, we forgot a plus 5 here. Let's not forget anything. No child left behind. So we have 2x plus 5, if you recall. Okay, that's better. So plus 5, we want to know if that's equal to 1/3 to the power of 3. So we need to combine these two fractions, so the denominator is 27. So negative 134 plus, now in this other fraction, we have to multiply top and bottom by 27. And we get 5 times 27, which again we know is 135, so that'll go here. We go back to my other color. We want to know if that's equal to 1/27, and notice negative 134 plus 135 is 1, so we get 1/27 equals 1/27, so it passes the check. All right, so if you want to write the solution set, it contains one value, and that's negative 67 over 27. All right, so I know that some textbooks, they like to give you these problems that have all these nice answers, but in real life, that's not usually the way it works out. So I actually prefer giving you problems where the answers will be more like real life. All right, so make sure that you're comfortable with this before we proceed. Again, sometimes you may not have time for a full check. Minimum amount of checking, make sure the argument or the base never become negative. Of course, the base should also not be 1. All right, so here we have another one. We're going to go ahead and convert this to exponential form. So we'll start with the base, which is 25 raised to the power of the whole log, which is going to be the exponent. So u equals, now on the other side we know that we always get the argument, like so. All right, so this is actually more practice like the items we did in the previous set. So we want to go ahead and write both sides as the power of the same base. It looks like 5 is going to work for us. So we'll write the 25 as 5 squared. And of course, we know we have the rule that says the nth root of x to the m equals x to the m over n. So we get 5. Of course, here the exponent is 1 to the power of 1/4. So on the left side, we can go ahead and use the power rule to turn that into 2u. We get 5 to the 1/4 on the right side. And of course, now we have the same base on both sides. If two powers are equal and their bases are equal, the exponents must be equal. So we get 2u is equal to 1/4. Now be careful with that, because that really is only true when you only deal with positive bases. Otherwise, take a look at this example. -2 to the 4 is the same as 2 to the 4 because they're both 16. But see, this does not imply that -2 is equal to 2. So this implication doesn't exist here. So be very careful to only make that deduction to go from this kind of a scenario to this scenario when you're sure that the bases are positive. All right, so now we're going to go ahead and multiply both sides by 1/2 to go ahead and solve for u, or divide by 2, same thing. Multiplying by 1/2 and dividing by 2 are basically the same operation. All right, so we end up with u is equal to 1/8. Okay, so I'm going to leave some of the checks for you, otherwise this video will never end. And but that's how you do it. In this case, our quick check of restrictions is not going to be really causing any problems, because on this side, remember, you can have log can have any output. The range of the logarithmic function is all real numbers, so there's no problem on this side. We always want to make sure we check these two values. These two positions are problems can occur, where problems can occur. On this side, you can have any kind of output is allowable by a logarithmic equation. All right, so make sure you can handle that, and then we'll proceed. All right, as we look back at some of the examples we just did, notice like in this one, the unknown is in the argument position. In the next one that we did, it was also in the argument position. In this one, it was in the exponent position, or the entire log position, so it was on this side. For our next problem, we're going to solve this logarithmic equation, noticing the fact that this time the unknown is in the base position, and we know that the base of a logarithm has to be positive but not equal to 1. So we're going to, so don't be confused with the fact that the x here is not playing the role of what the x is playing in our general definition. You have to be very flexible with that kind of change in mathematics. All right, so do keep in mind x is playing the role of b. So we know that the restrictions on the value of x are the fact that x should be greater than 0 and x should not be equal to 1. So with that in mind, we proceed with solving. So now we're going to use this definition of logarithms to convert this logarithmic equation to its exponential equivalent form, and we end up with x to the power of 3 equals 24. Now, we do know how to handle these based on previous work, and we know that to get x, if we know x cubed, we have to, of course, take the cube root of both sides, and that's what we will do at this point. And we end up with cube root of x cubed equals cube root of 24. Now, on the left side, we know that the nth root of x to the n equals x, as long as x is positive, right? Now, if we don't know that x is positive, right, which we do know in this case, but if we didn't, we would have to be much more precise with that definition. We would want to say the nth root of x to the n equals x if n is odd, and absolute value of x if n is even. But given that x is positive, we don't need to worry about this more complex definition for the nth root of x to the n, and we can just use the simple version which says the nth root of x to the n equals x. Of course, even if we were to use this and worry about it, we would still be okay because we're dealing with an odd index. So we do notice that we end up with x equals the cube root of 24. So now we check it against the restricted values that we have to worry about, and we notice that this in fact is positive, and it certainly is not 1. So it passes the restriction check. So we can go ahead and accept it as a solution. All we need to do is make sure that we simplify it. Now, if you know how to do that without finding the prime factorization, you can proceed. If not, you can quickly find the prime factorization of 24. The smallest prime that goes into 24 is 2. When we divide, we get 12. Again, 2 gives us 6, 2 gives us 3, and 3 gives us 1. So we notice there is one perfect cube hidden inside 24. We put that in the first radical, the perfect cube radical, and then the next one we put the non-perfect cubes factors of 24. So notice that, so 8 goes in here, and what's left? There's only 3 left, right? So we put 3 in here, so we end up with 2 times the cube root of 3 as the value of x. So that's the simple version of the answer, or the simplified version. So that's what we get when we try to solve this equation for x. Make sure that you can handle that, and then we'll proceed. All right, so our next problem is rather similar, but there will be a minor twist we'll have to deal with. So again, we'll look at the x, and we realize that the unknown is in the base position. So again, it has to be positive but not 1. So the restrictions are that x should be greater than 0 and x should not be 1, right? So we go ahead and proceed by using the definition of logarithms to convert this to exponential form. So we end up with x squared equals 50. So notice that when you apply the square root property to solve this, right, we get x equals plus or minus square root of 50, right? Which is, of course, equal to plus or minus, if we break it up, this time we know 25 is the largest perfect square factor of 50, and that leaves a 2. So we get plus or minus 5 radical 2. So we notice right away that if we split that into 2 separate solutions, x equals 5 radical 2 or x equals negative 5 radical 2, this one right away fails this requirement, right? Because negative number is obviously not greater than 0. So this one we reject. And this one, however, so in other words, this one fails the restriction check because it's not positive. This one is positive and it's not equal to 1. So this one passes the restriction check. So be very careful. If this were just an equation in itself that we were solving, we would have accepted both of those solutions. But because we're solving this equation here, and x is the base of a logarithm, we know that we must reject any negative choices, or 1. So, or even 0, right? So we want the base to be positive and not 1. So there's only one solution. If you want to write it as a solution set, we would only include the 5 radical 2. And that would be it. Okay, so just a little minor twist, but it's important to pay attention to it. So again, make sure you can do this before you proceed. All right, next we want to take a quick look at a few facts that pop right out of the definition of logarithms. One quick fact is that, notice if you take the log base b of any number b, that's just going to be 1. Because remember, when you see log base b of b, what do you ask? You say b to what power? There's an invisible exponent there that gives you this, right? And that's going to be the answer for the log. So b to what power gives you b? Of course, that's going to be 1. So why is this true? Because b to the power of 1 equals b. Just take this and put it in logarithmic form, and you'll see that you end up exactly with this equation here. All right, so for example, if you see log base 7 of 7, that's a no-brainer. You know the answer is going to be just 1, right? It's just common sense anyway. If you understand the definition of logs, this is almost not worth mentioning, but these come in kind of often and make appearances, so it's good to be very comfortable with them. Or for example, if you get log base x of x, same business. Could be variable, it could be constant, any way you want it. All right, so the second fact is that if you take the log any base, the base doesn't matter as long as it's a legal base, of course, of 1, you're always going to get 0. Why is that true? Because look, b to the power of 0 equals 1 for any b, right? So that's why it's true. So for example, if you see log base 100 of 1, there's no work needed here. You basically need to know that the number, the exponent, you need to raise 100 to the power of to get 1, which is what's going to go here, which is what the entire log is. Just that exponent is going to be 0. All right, so if we take log base u of 1, it doesn't matter what u is. As long as it's a legal value, you know it's going to be 0 as well. All right, the next fact is very kind of similar to this, but this time we're saying b to what power? Remember, we're looking for that invisible exponent that when we raise the base to the power of, we get the argument. So think about it. B to what power gives b to the x? You answered it, right? Just x. That's it. So for example, and why is this true? Because b to the x, b to the power of x is the same as b to the x, okay? So for example, if you have log base 7 of 49, yeah, it's not in that form yet, but notice I can always write this as log base 7 of 7 squared, which I know now by this rule, which you should not just memorize but fully understand, is 2. So that's an interesting way of dealing with that. Or if you have, say, log base 1/2 of 1/8. You can always write that as log base 1/2 of 1/2 cubed. And now you can see you're in this form, aren't you? 1/2 and 1/2. So you should just get 3. All right. The last one might look a little bit weird at first, but when you think about it, it makes total sense, because we're saying b to the power of log base p of x is x. Well, look, just from a purely substitutional point of view, remember this basic equation that we've been using all video, right? Notice that we say y equals log base p of x on this side, and on that side we have x equals b to the y. So all we've done here is we've taken the y, which is the same as log base p of x, and we've put it instead of the y here. So we end up with b to the power of y, which is log base p of x equals x. So that's just from looking at it and doing a substitution, so it makes sense. However, a deeper understanding tells you b to the power that you have to raise b to the power to get x should, of course, give you what? Give you x. Think about that for a few minutes. See if that makes total sense to you. Because what is log base p of x? It's that power of b, right? That gives what? That gives x. So if you raise b to that power of b that gives x, of course you're going to get x. All right, so for example, if somebody gives you 10 to the power of log base 10 of 50, this is like a gift. There's not a whole lot to do here. Since these two bases are the same, you know the answer is just going to be 50. Or if somebody gives you j to the power of log base j of z, I guess in honor of jz, you just get what? You just get z. All right? So that's a quick summary of these 4 basic facts that pop in from time to time. So you really want to be familiar with them and be comfortable with them, okay, before we proceed. We're almost done. We're just going to look at a couple of graphs and call it the day. All right, so suppose somebody asks you to graph y equals log base 2 of x. Now, you could, of course, make a table of values where you give x values and then find corresponding y values, which means you're going to have to take logarithms. Or you could do what's easier, which is just to find powers. So what we do is we take this equation and we write it in its exponential equivalent, which is going to be x equals b to the y. In this case, x equals 2 to the y. It's the exact equivalent of this equation. So if we graph this equation, we've also graphed that equation. So, but the only catch here is you have to make sure you start by giving y values first. So you're taking care of this column first. You're picking these, then you're plugging these into here to get the corresponding x value. So we're working kind of backwards from the way we're used to working, right? Usually we give x values and then substitute to get y, but now we're doing the opposite. We're giving y values and substituting to get x. So when you substitute -2, you get 2 to the -2, which is, of course, 1 over 2 squared, which is 1/4. Substitute -1, you get 2 to the -1, which is 1 over 2 to the 1, which is 1/2. Substitute 0 for y, you get 2 to the 0, so x is going to be 1. Substitute 1, you get 2 to the 1, which is going to give you 2. 2 will give you 2 squared, which is 4. Plot those, and you get this nice looking graph here. Notice this time, it's not the x-axis like in the case of the exponential function, which is the asymptote. It's the y-axis, and it's not a horizontal asymptote, it's a vertical asymptote. That means a line where the graph comes arbitrarily close to. Remember what that means? That's a technical term. That means it comes, you can get it as close as you want to get it. You can give me any positive distance and say, hey, I want you to bring it within a millionth of an inch. It's doable, right? However, it will never actually cross it. So that's what is meant by an asymptote. So this graph of the logarithmic function has a vertical asymptote. The equation, of course, is just x equals 0 because that's the equation of the y-axis. All right, so let's go ahead and take a look at this and put it next to the graph of the exponential function, see if we notice anything. Okay, so here we're putting the graph of log base 2 of x and 2 to the x on the same Cartesian coordinate plane. We did this in the last video and we did this one in this video. Notice the beautiful relationship between them. They are indeed symmetric with respect to the line y equals x. If you remember from the last video, functions that do that are inverse functions. So they switch domain and range. Notice that the domain of the red graph, which is y equals 2 to the x, is all real numbers, and that's the range of the blue graph. They switch domain and range. The range of the red graph is all positive numbers, real numbers, and that becomes the domain of the blue graph. So they are precisely inverse functions. In fact, we can easily prove it in the case of these two. Remember, if you have two inverse functions and you start with an input, apply one of the functions to get an output, then the inverse should take you back to that. So if you follow those two functions back to back in the form of composition of two functions, start with x, apply f to it, and then apply f inverse to that outcome, you should get back to x. And notice that we do, because f inverse of f of x just means, in this case, we're calling the log base 2 of x the f inverse function. So it just means f inverse of log f inverse of 2 to the x. So that means plug in 2 to the x where you see x in this expression. So if I were to add one line here for you in writing, so you have f inverse of f of x is going to be f inverse of, notice what f of x is, it's 2 to the x. So it's going to be f inverse of 2 to the x, which is going to be apply the action of f inverse to this input now. The input is 2 to the x. So you get, instead of x, put 2 to the x. So you get log base 2 of 2 to the x, which is, as we learned a minute ago, x. Or if you go the other way around, you have f of f inverse of x. That means f of, okay, what is f inverse of x? Log base 2 of x. Now apply the action of f. What does f do? You feed f something, it raises 2 to the power of that something. So it's going to do the same with this input. So it's going to take 2 and raise it to the power of log base 2 of x. Recognize this from the previous screen. That's also just x. So here we showed it for the case of base 2, but imagine replacing all these 2's with b. Then you have proven it for all exponential functions and logarithmic functions of base b. So yes, in general, these functions are inverse functions. You can see in their tables too how the outputs here are the inputs here, and the inputs here are the outputs here. You can see the beautiful relationship also in these ordered pairs, Notice how the x and y are switched. That's symmetry with respect to the line y equals x, which is unique to inverse functions. Do notice that when the base is greater than 1, the logarithmic function is an increasing function. Just as with exponential functions, when the base is greater than 1, they're increasing. See, the values of y keep getting larger and larger. Same happens here. Not, of course, as fast as the exponential function in this case, but they are increasing. Now let's see what happens if we look at a base value between 0 and 1. See what happens when you take a base value between 0 and 1. The logarithmic function becomes a decreasing function. And that's exactly what happened with the exponential function as well. All right, and these two, log base 1/2 of x and y equals 1/2 to the x, are obviously also inverse functions. All right, these beautiful graphs and hopefully the associated intuitive understanding bring us to the end of this video finally. I know it was a rather long one. Sometimes it cannot be helped, unfortunately, but I hope you learned much and that you will practice much so that it truly becomes your own knowledge and understanding. All right, be safe until our next video.